All right. Sorry, I had a last minute tech thing pop up. Okay, so hopefully Frank can hear me now. Yeah, so this next lecture is going to be much more combinatorial than the first one, but we're going to build on some of the things that Frank told us about Grassmannians, but think about this cohomology ring in a different way using Schur polynomials. All right, so last time Frank told us about the Grassmannian of k-dimensional subspaces of C to the m. And in particular, we saw that we can think about this as being this sum, these formal linear combinations of the Schubert classes. And what we really want to understand is how to take two Schubert classes, multiply them together, and expand them out in this Schubert basis. And we got a proof of the PRE formula in particular, where we're multiplying by a special partition that's just a single row. Okay, up, let's begin. Slow, there we go. Okay, so in this lecture, we'll take a more combinatorial and algebraic perspective. So we'll start by discussing Schur polynomials, and then we'll move on to some discussion of tableau combinatorics. And in particular, we'll look at this Littlewood-Richardson rule that tells us completely how to compute these Littlewood-Richardson coefficients. Okay, so starting with Schur polynomials, we can look at this thing, this Young diagram of a partition, which we saw in the previous lecture, where we're taking this partition. I'm writing mine in reverse order, so weakly decreasing sequences of positive integers. And we just put like 4 boxes in the first row, 3 boxes in the second, 2 in the third, and 2 in the fourth, just like this. And so we can start to fill these boxes with numbers, and we're going to fill these boxes with numbers in a very particular way. Most often we'll place positive integers in these boxes, and then we want along rows for things to be weakly increasing, and along columns things to be strictly increasing. And when we do this, we get a monomial weight by just looking and seeing how many of each number shows up in this object. So for instance, here we have 2 1s, so we get an x1 squared. We have like 3 4s floating around, so we get this x4 cubed. So everyone with me? Okay. All right, and then the Schur polynomial is just going to be a sum. We are going to fix some number of variables, and we're going to get this sum over these semi-standard Young tableau of shape lambda with entries in 1 through k. And so as an example, if lambda is this partition 2, 2, which looks like this 2 by 2 box, and k is 3, I've written out all the different semi-standard Young tableau that you can have and their corresponding weight monomials. Okay. So we have a big mix of, I think, like people who are new to Schubert calculus and experts in the room. So this is definitely, I am aiming for the people who are new to Schubert calculus. So I hope by the end of this lecture that you can walk away computing some things. So what I want to do is I want to give you time throughout the lecture to actually compute some things. So the first thing you are to try is to compute this particular Schur polynomial. Feel free to talk with your neighbors. If you, yes? Oh, yes. Yes, I can do that. That would be helpful. Okay. Yeah, sorry. So compute this particular Schur polynomial, and then here again is the definition to help you out. So if you are an expert, I'm deputizing you as a helper. Hopefully you're sitting near someone you can help. If not, yeah, you can move or. So I hear chatter. How are we doing? Okay, we ready to move on? Okay. So, yeah, Looking here, there's just 3 different tableaux. So since I limited us to the variables 1 and 2, this left-hand column was really like rigid. It was determined. To get this strictly increasing, we had to put a 1 and a 2. But then we had more flexibility for these other boxes. For things to be weakly increasing, these were the options that we had. So this gives us our Schur polynomial. Okay, so a polynomial is symmetric if any way that we could permute the variables, we get the same polynomial back. So for example, this polynomial here is symmetric for any way we could permute these 3 variables, x1, x2, x3. We're going to get the same thing back. And it's a fact that Schur polynomials are actually symmetric polynomials, and they're a basis of this ring of symmetric polynomials. You can multiply 2 symmetric things, it stays symmetric. You can take linear combinations of them, stays symmetric. Okay. All right, so one of the exercises is going to be, so this is an exercise for later, is going to be that you will show that Schur polynomials are symmetric by finding little involutions that swap i's and I plus 1's in these tableaux in a way that does this thing to the weight, where if you take the weight of your original tableau and you apply this simple transposition si, which exchanges I and I plus 1, you get this nice action on the weight where you switch xi and xi plus 1. So here I've drawn just a very, very tiny example where here we're exchanging, if we exchange x1 and x2, like these monomials go together, and their tableau also go together. If we exchange this x1 and x2, nothing happens. So you're looking for little local swaps in any 2 adjacent numbers that will show that this is symmetric in those variables, and then you can get symmetry in any permutation. Okay, so there's some very special symmetric polynomials that play important roles in understanding this ring structure. In particular, we can talk about elementary symmetric polynomials. So these are sums over monomials where we have this strict increasing property in these indices, and so we get something like this. So for E2, like we can take this index 1 and 2, and we get x1, x2. We could take 1, 3, we get x1, x3. We could take 2, 3, get x2, x3. And there's also homogeneous symmetric polynomials where we relax this strict inequality and we make a weak inequality instead. And so here I've written out h2 in 2 variables, and it looks like this. So one thing that you can do now, again as a quick sanity check, is explain why these EAs and HAs are actually Schur polynomials. So again, chat with a neighbor, see if you can spot why these things are special cases of these Schur polynomials. Anyone feeling brave? Anyone want to share? Yeah. Yeah, so the elementary symmetric polynomials, these EAs, are just fillings of columns. So that's the strictness that we're seeing. And then what about the H sub A's? What sort of fillings are we doing? Anyone new? Yeah, this one. Rows, yeah, exactly. Okay, so there we go. So these are very special cases, but then we can really build this up and multiply things out and get these elementary and homogeneous symmetric functions for any partition. But we won't talk about that today. Okay, so one thing that we can do with these homogeneous symmetric functions is we can express the Schur polynomial as a determinant of these homogeneous symmetric functions. And this thing is called the Jacobi-Trudi formula. And so there's a lot of indices here, but basically this is depending on our tuple lambda. And then we're taking like lambda 1s in the first row, but then we add 1 in the second column and so on. here we start at -1, then we go 0, and so on. And the whole point of this big formula that I'm showing you is that we can write S lambda as sums and products of these HAs. And so really, algebraically, like, these HAs are really determining this multiplicative structure. If we can understand how to multiply by HAs, we understand the whole shebang. Okay. And so in particular, like, what we were after in this first lecture was understanding the structure of the cohomology ring, of the Grassmannian. And since Schur polynomials are a basis, we also want to understand, well, what happens when we multiply two Schur polynomials and expand in this Schur basis. And what we get are the same Littlewood-Richardson coefficients that we saw from the Grassmannian. And really, like, one way to think about this is that Schur polynomials, they also satisfy the Peori rule that we saw before. So this geometric situation and this algebraic and combinatorial situation are working together in parallel. Okay. All right, so next we're going to talk about some operations on Tableau. So in particular, we're going to think about insertion algorithms. Okay, so what we can do is we can take a tableau and we can try to, like, shove a number into this tableau in a certain way. And so what we're going to do is we want to, at every step, preserve semi-standardness. But this 3 really wants to belong to the first row. So what it's going to do is it's going to look for the first number that's bigger than it. And it's going to go in and say, I'm going to take your seat. And so this 4, it's going to turn into a 3. And then now the 4 needs a home, so the 4 is going to try to go into the second row. Okay. And then we're going to repeat this process. This 4 is going to go into the second row, and it's going to look for something where it has precedence. So it's not going to bump any of the other 4s, because it's basically tied with those. But it's going to take this 6, and it's going to bump the 6. And so now the 6 needs a home, so it's going to go into the third row somewhere. And then here, the 6 had nothing to actually bump in this row. It's not taking precedence over anything else. And so what it's going to do is it's just going to kind of sit down at the end of the row. And then we get a new tableau out of this process that is still semi-standard, but it has one more box in it. And now its weight just differs by multiplying by x3. Okay. And then we can also do something where we can, like, as note keeping, we can keep track of what happens as we insert. And so we can think about, like, this byword where we're going to insert this bottom sequence into a tableau. And then we can use the top row numbers to kind of mark where the new boxes happened. So in particular, if we take this tableau here, and we go and we insert 1 into it, this 1 from here, we get what we see here. So we get this 1, it goes in, it bumps the 2, and then the 2 goes down here. So sorry, I keep accidentally clicking forward. It's very sensitive. So the 1 bumps the 2. The 2 wants to go into this row, and it bumps the 4. And then the 4 pops out here. And so we get this tableau here. And then we mark with a 1 that we added that box. And then next, we want to take this 2, and we want to insert it into the bottom row again. So we're going to take the 2. We're going to insert it in here. And when we do that, the 2 is going to bump the 3. So I should write a new tableau so that it's more visible. Okay. So we have 1, 3, 2, 4. We have our recording tableau. And so when we bump this 2 in, it's going to displace the 3.
You're bumping the 5.
What am I doing? Oh, I'm bumping 5 in. Thanks, Frank. Okay. Thank you. Yeah. I want to bump the 5 in. Okay. this is that same chalkboard. When you touch the chalkboard, all your brain cells go away. Oh, there we go. There we go. Okay. Okay, so we're gonna bump the 5 in. Thank you, Frank. So the 5 just goes and sits out here. So it had nothing that it takes precedence over. And then we're gonna mark that we added that box by putting a 2 in. And then in this next step, we're going to try to bump the 2 in. And so when we start with this tableau here, we get 1, 3, 5, 2, 4. So when we bump the 2 in, the 2 takes precedence over the 3. The 3 comes and it wants to sit in the second row, and it doesn't take precedence over anything, so we just add a box for it to sit in. And then there will be a slightly better looking picture momentarily, but we'll just write this out. So we've got a 1, a 2, and then we record that we bumped that 2 in with a 3. Okay, so this is our insertion, algorithm, and recording tableau. Okay, so we get this here. Any questions? All right. So a particular important special case of this is we can interpret a permutation as a byword. And so we can like write out just 1, 2, 3, 4, and then we could do something like 2, 1, 4, 3. And so this just tells us, well, 1 maps to 2, 2 maps to 1, 3 maps to 4, and 4 maps to 3. And so this theorem of Robinson-Chenstead says that this insertion map, where we have this insertion tableau and recording tableau produced from a permutation interpreted as a byword, produces a bijection between permutations of n and pairs of standard Young tableau of the same shape. So a standard Young tableau is just a semi-standard tableau where now we're using the numbers 1 through n, each of them once, if the shape has n boxes. So the number of permutations is n factorial, and so we get this numerical consequence that n factorial is equal to the sum over partitions of n of the number of these standard Young tableau squared, indicating that we have these pairs of the same shape. Now, another thing that this sort of bumping algorithm gives us is a way to multiply tableau together. And so what we can do is we can take the word of a tableau by reading in kind of a funny way. So we're going to read its entries along rows from left to right, starting with the bottom row. So what are we doing here? We're starting at the bottom row, and we're going to just like read this 7, 9 and write them down. Then we're going to read this 5, 6 and write it down. Read this 3, 4, 4, write it down. Read the 1, 1, 2, 4, write it down. Now, what I've done is I've drawn these bars in these places where the numbers decrease. And why I've done that is it's kind of an artificial thing, but we can just use that to reconstruct the original tableau from the word that we sent it to. So this tells us where we had the change of rows. And then we can define this multiplication on tableau, t times u, by inserting the word of u into t. And so then we can really think about this tableau ring, where we're taking these formal spans of tableau, and we have this multiplication that extends by linearity, where we've defined it just as before, inserting one tableau into another. And there's a nice ring homomorphism from this tableau ring. Oh, sorry, I switched my indices there. It should be okay. By mapping a tableau to its weight. And so the idea is that if we see some structure in this tableau ring, then we can use it to extract structure downstairs in the ring of symmetric functions. Okay, so in particular, we're going to define this special element that's just a sum over semi-standard tableau of a fixed shape. And the image of that element is going to be the Schur polynomial. Okay, so here, this example is going to be, I don't know, a little more extensive. Maybe you can you can subdivide the task among the people near you. But let's try and actually like compute this product in the Tableau ring. Okay, so we'll do just 2 variables to make it a little bit less painful. So the first thing you're going to want to do is figure out like which tableau are we multiplying, and then write out a little multiplication table. Okay. Yep. So I think this one. So you're going to practice some bumping. And then hopefully once you've written out these tableaux, you'll have noticed something. If you have questions on how to get started, flag me down. like actually learning and engaging, so I don't want to cut off the conversation. I just want to like pop in momentarily. So let's see, what was this S box of 2 thingy? What does this really look like? What am I summing together? Yeah, so we're having like a box with a 1 in it plus a box with a 2 in it. So these 2 tableaux summed up together. And then we've, I think, seen this critter before basically, but we were just doing the tableau separately. But this S box of 2, we're going to have 3 tableaux. So we're going to have our 1, 1 plus, or maybe we saw something similar, but not this exact one, but something like this. Okay, and so now to multiply these things together, you're going to just try and basically like FOIL it out like you would, but now there's just like tableau floating around, but that's okay. Just like use your distributive law that you're used to. Okay, so I'll let you go a little bit longer and then we'll come together and see what we see. Not everyone has been able to multiply like everything together, but I'm hopeful that at least people have internalized, okay, we can take these 2 tableaux, we can kind of bump this word into this other tableau, and that's how we multiply. So I'll just like skip to the answer, or maybe a multiplication table, and then we would sum up all the tableaux that we get in this thing here. And so I've kind of like written the punchline up here, but you might notice that we can group the results. So we have like these tableaux here are really, if we sum them up, we get this thing here. And these tableaux here, if we sum them up, we get this thing here. And so the upshot is that what we're really seeing out of this is we're seeing like we're getting not only the right monomials when we multiply in this way, but we're getting the right tableau when we multiply in this way to tell us what this Schur expansion should look like. Okay, so going back to Pieri in particular, yes, so this, let's see, Frank told us about both the interleaving condition and the sort of visual condition of getting partitions by adding a horizontal strip. So this comment was just to make sure we had that combinatorics. But then a proposition is if we take t times u, where t comes from a semi-standard tableau for mu, and u comes from a semi-standard tableau for a horizontal strip of length a, then when we do this tableau multiplication, we're going to see at the level of pairs that we're going to be getting all of the tableau over lambda that we get from mu by adding a horizontal strip of length a. And so in other words, we're able to, again, see this algebraic thing we were hoping would happen in terms of the combinatorics of the tableau. Oh, okay, so that's just the Peary rule, but there's a whole lot more multiplying that we can do. And so we're going to talk about something very special that's called the Littlewood-Richardson rule. Okay, so we've seen a little hint at this, but we can talk about these things called skew semi-standard tableau. So what's a skew shape? What we do is we take kind of a big partition, and then we take a littler partition where all of its boxes are contained inside of the big ones. And so we can think about it as just like taking the little partition out of the big one. And here I've just like X'd off those boxes. We're just not allowed to think about them. They're just like holes. So now what we can do is we can start to fill this thing with positive integers in such a way that the rows are still weakly increasing and the columns are still strictly increasing. So this thing that we get here is called a skew semi-standard tableau. Okay, so a skew semi-standard tableau has content mu if it has mu I entries that are I for all I. So this one here, for instance, has content mu equals 3, 1, because there's 3 1s and just 1 2. And then there's this special property, this ballot property. T is ballot if it's reverse row word, this reading word that we saw from before, but flipped backwards, has this property that in any initial truncation, there's at least as many i's as I plus 1s. Okay, so this takes a little bit more to unpack. So let's remember this row reading word that we had from before. It was 1, because we're starting from the bottom and reading left to right. And then we had this 2 from this row. There was just nothing in the third row. So we just like don't write anything down. And then in the first row, we have 1, 1. So this was row of T. And then now we're going to reverse. So we get 1, 1, 2, 1. And then we want to make sure, as we look at like these partial sequences, so like 1, 1, 1, 1, 1, 2, 1, 1, 2, 1, each of these have as many 1s as 2s. Here we only have 2 variables, so there's nothing else to discuss. And so you can see here, well, yeah, it's satisfied. Like we might worry, oh, there's a 2, but we're already like 3 1s there, so we're good. Okay, questions about that condition? Okay. So what the Littlewood-Richardson rule says is that the Littlewood-Richardson coefficient C mu nu lambda counts the number of skew semi-standard Young tableau with content mu that are ballot. So here's an example. We can take, so you want to think about taking, this is our big partition, this is the thing we're skewing out. In this example, they're both the same shape, but you can have other things as well. And then the content of this is going to tell us that we have 2 1s and 1 2. And so if we try to fill these in a semi-standard sort of way, well, here these boxes are like, yeah, it's not so important because nothing's like side by side or below anything. But the ballot condition here, our reverse words are 1 1 2 and 1 2 1, and they both satisfy that ballot condition. So these are our Littlewood-Richardson tableau. These tell us that this coefficient is 2. Okay, so I'm going to do another thing where I've like taken away the things that the notes you need to do the you try, but I'm going to ask that you try to use the Littlewood-Richardson rule to compute the Schur expansion of this product. Here I'm starting to be a bit lazy about the number of variables. Really, the only tableau that are contributing are ones with at most as many rows as the number of variables, but you can just kind of try to play with the Littlewood-Richardson tableau and see what you can see. And if you happen to go very fast, you can see, oh no, yeah, I had tried to fix this slide, and I think this slide didn't get fixed. Okay. But I meant, spoilers. I meant for you to compare with this other one here. What happens if you switch the order? Okay. So this is another one. Maybe you won't compute the whole example, but especially these people who are new to Schubert calculus, welcome. I want to give you a chance to try to compute, to try to internalize these rules. Yes, yes. Okay, so write down the tableau, and then I'm going back to the Okay, so anyone want to share a tableau that they found? So here, we're going to think about, if we're multiplying this way, we're going to think about kind of skewing out these two boxes. And then we need to try to add 3 more boxes to this picture. I'm going to try something that won't work. So if I try to put like 3 boxes like this, and now when I try to fill in the content, so the content I need to have 2 1s, and I need to have a 2. So if I filled this in, why does this one not work? Semi-standard, that seems good. Yeah. It's not ballot, so it doesn't have this property that this reverse reading word, this 2 1 1, it starts with a 2. We're already sunk at that initial truncation. We have more 2s than 1s. Okay, so that one's bad. So I did the easy thing, a bad tableau. Anyone? Oh, no. Okay, maybe I'll give it up. So yeah, looking here, we have these tableau here. And again, sorry, these 2 should have been swapped. I think something went a little haywire. Okay, but these are, hopefully I found them all, our Littlewood-Richardson tableau that let us compute this Schur expansion when we multiply these 2 Schur polynomials. Okay, are there any questions about that? Yeah. Oh, let's see. Uh-huh. Oh, a 1 at the bottom. That's a great, yes. I love that question. Okay, so the question was, for the 1 at the top, like, did you want maybe this, so skew, 1. Did you want like a 2 here and a 1 there? No. Okay. Oh, the same shape with 3 1s. Oh, I love that question too. Okay. So the same shape with 3 1s. Whoa. So if this 2 was a 1 instead, what fails is this content condition. Yeah, so we need content mu, and this means that we must place 2 1s and 1 2. Yeah, yeah, I love that question because that's like a question you would have when you see this rule the first time. Okay, any other questions? So the point of this very magic rule is that we can compute these structure constants using combinatorics. We don't have to like do geometry. We don't have to do linear algebra and like multiplying things out and like gathering up terms and yeah. We have a basis. We could use linear algebra, but we can just use this combinatorics here. We can put numbers in boxes and we can compute these structure constants. So it gives us a new way to think about the structure of this cohomology ring. Okay. So one exercise for the exercise section, more as just a quick check, is how do you recover the Peori formula from the Littlewood-Richardson rule? And there's also kind of a dual sort of formulation to the Peori rule, where instead of multiplying by a horizontal strip, we multiply by a vertical strip. And so one task for you to do is to think about how can you have a rule for multiplying by a vertical strip instead of a horizontal one. You can take your best guess, or you can just try to recover it as a special case of the Littlewood-Richardson rule. Okay, so the big idea behind this Littlewood-Richardson rule is that we can take a tableau T of shape mu and a tableau U of shape nu, and we can map this pair to its product in this tableau ring. And the size of the fiber of any tableau V of shape lambda is going to be this Littlewood-Richardson coefficient. So there's more machinery than I wanted to get into today behind this, but this is the big picture idea that the individual tableau, when you're multiplying, they don't really matter so much. All that's really important is the shapes. And then I think unlike Frank, I was like maybe short, so I should have donated some of my time to Frank. But maybe this means that we just have more time to work on lots and lots of exercises. So I'll go ahead and stop there.